Hello, everyone. It's nice to meet you here. I'm very happy to share with you some of our results on federated learning and AI. First of all, artificial intelligence today is facing a great challenge from data fragmentation and data silos. Data are located on different devices, have different owners. It's difficult to merge them into a central location because of several reasons. One reason is that people are very, very concerned about privacy. As this news title suggests, society is fed up with privacy leakage. As a result, places like Europe have introduced laws such as GDPR to safeguard data security and privacy. And this is a worldwide effort. For example, in China, such effort has ended in a publication of a sweeping data privacy and security law, which actually is formally published this month. In many ways, it's very similar to GDPR. States very strict fines for those who violate the unauthorized use of individuals' data. And as a result, we introduced federated learning. The idea of federated learning is that even though data are distributed at different locations and data may have different distributions, that is, they are non-AIED, we can still build a general model which take into account the knowledge from different data. As the figure in the middle suggests, even though we cannot exchange data directly between these two corporations, A and B, we can still, by exchanging some encrypted model parameters, we can build a global model, which is really a sum of the parts. Part of the model locates at site A and another part at site B. And so generally, the philosophy of federated learning is to build a common model, a general model among several data owners, while allowing the data at each site to be located only in that site and will not need to travel out. And still, the model can grow. And the way to do this is to allow different parts of the model, that is, different sites of the data to share some encrypted parameters. And this technology is a combination of multiple technologies. As a result, it has different names, such as federated machine learning, collaborative machine learning, distributed, privacy-preserving, multi-party learning, and so on. And as a result, it uses different technologies from different areas across computer science and beyond, such as privacy and security, model design and AI, communication efficiency and network protocol design, incentive mechanism design, distributed machine learning, and so on and so forth. Now, I should mention that we have published a first textbook called Federated Learning to cover this area, to give people a broad view. And this has been published in both English and Chinese. Interested readers may wonder, well, we have such technology as differential privacy already. Why do we need to introduce a new technology such as federated learning? as we know, differential privacy is to introduce a level of noise into a data store so that when communicating the data directly with another source, the other source cannot tell any individual's private data. And this is guaranteed from a probability distribution point of view by introducing the noise, and you cannot distinguish between the two data distributions. Although it has a certain level of privacy protection for individuals, it's still not 100% guaranteed because it's a probabilistic notion. Second of all, by introducing noise, it hurts the model accuracy. And thirdly, introducing noise will further increase the bandwidth between different parties in the communication channel, which actually is one reason why we want to use federated learning, is to reduce this bandwidth. Think in terms of, let's say, a satellite communicating with a server. You cannot use communication between raw data, not to say raw data compounded with noise. So with this in mind, some people may ask whether introducing noise into gradient information is enough to protect the data privacy. The answer is no. If two parties communicate gradient information, it's still not enough to protect the privacy of the data, because it's possible, as this work, which was published in 2018, show it's still possible to reconstruct the original data, even if two parties only communicate by the gradient information. Okay, so we have to marry secure computation methods such as multi-party computation methods, homomorphic encryption, garbled circuit, secret sharing, and so on, with distributed machine learning, with special machine learning such as transfer learning, to allow non-AIED data and model parameter protection. And most useful is homomorphic encryption, which allows distribution among arithmetic operations between encryption and polynomial computation of the parameters. So when this can be done, we can then formulate for any nonlinear computation some kind of linear approximation, and therefore by using homomorphic encryption, we can protect not only the data but also the parameters. Then we should look at how federated learning can be used in distributed learning settings. There are several settings we summarize into 3 general settings. The first one is different parties hold different samples, but they share mostly the attributes or features. In such a scenario, we have what's known as horizontal federated learning, and different parties can communicate their local models, the parameters of local models, in order to update them. The algorithm in this setting takes advantage of the encryption mechanism, the communication distributed machine learning methods, as well as the parameter update method. One practical example is Google's Fed average algorithm, which combines the model updates from different devices into a general model, and then use the general model to further influence the local models in this cycle. And this has been applied to Android system. Another setting, when we have multiple organizations such as banks and hospitals, we have partition not by samples, but by features. Different organizations may have different features, but they work more or less on the same set of users. In such a setting, we have vertical federated learning. And this learning can be applied to a setting when, say, on one hand, we have a bank which wants to enhance its credit model. On the other hand, we have retail shops or even internet online shops which have a lot of user behavior information but not credit information. So by working together in a vertical setting, they can further expand their feature space and in order to build a more robust model. And in doing so, they have to introduce an extra step in finding out their common users without revealing their individual users to the other site. And this can be further done using what's known as entity matching under privacy preservation. Now, if we can find out these users, we can build a common distributed model by exchanging encrypted model parameters by following the steps on the right-hand side of the slide. And in the inference time, when a new user comes, the parties can further exchange encrypted ID and the new user information, and in computing a global result. And the global result can be computed without revealing the new user information to the other parties and revealing the model information to the other parties. Now, usually in this kind of study, it's important to provide security analysis to show that indeed no local information is leaked out. Now, by following this methodology, we can then update any centralized machine learning algorithms. So here I show a version in federated learning for XGBoost, which is a decision forest model. Now, the vertical model is known as secure boost, and the horizontal model is also designed in GBDT version. Now, the third setting is when we don't have much overlap either on the sample dimension or on the feature dimension. Then we can use transfer learning to transfer the local data to a common subspace and perform federated learning in this subspace. Now, another dimension in federated learning is going beyond the machine learning side into economic side. That is, when we have an ecosystem, everybody is contributing some of their model knowledge into the group. The question is how we should fairly distribute the profit into different individual parties in order to incentivize these parties to contribute continuously and contribute more to the parties. And this, we can introduce some game theory motivated models, okay, to find out the utility of such a model. A survey paper was recently published and was done by many front runners in the research field. It's highly recommended. It's freely available on the archive. It's called Advances and Open Problems in Federated Learning. There are also a large number of applications in a very diverse range of fields. In finance alone, we have seen examples in anti-money laundering, in internet and banking for risk modeling, in insurance pricing, and in intelligent marketing. In credit rating, for example, people care about a larger and larger feature space in order to boost the model accuracy. So it is advantageous to introduce more and more data sources into the big data ecosystem. And so these data sources may involve financial companies and non-financial companies. In one sense, you can have hundreds of these companies, but everybody is concerned about their data privacy. They don't want to share the original data. And so in this setting, federated learning can help build a general model which can enhance the accuracy in credit rating while preserving privacy. So another setting is computer vision. In construction site safety insurance, we have introduced federated learning. This is horizontal federated learning to boost the accuracy of the computer vision model without sacrificing the local privacy. In recommendation systems, especially in advertising domain, we can have multiple parties working together without sharing the original data. And they can do this by using a matrix decomposition model. And this model can allow different parties to share a common user matrix while preserving their local data. In speech recognition, we have different data stores hosting different language models, and we can boost the language models of each party by letting them collaborate together, again, without exchanging the local speech data, which has a lot of private information. The result of the federated learning model reduced the error by 10 to 20%. The federated learning system indeed relies on a ecosystem. So in this regard, we have built a large ecosystem using SaaS, which is a cloud-based system. So far, we have accumulated about 40 million queries with about 500 organizations involved in the ecosystem. And we have different standards to ensure that they communicate well. Now, one application is in the supply chain industry for inventory capacity prediction. And also in edge computing for example, satellite to build a satellite ecosystem, or unmanned vehicle can build a autonomous vehicle ecosystem. Fed vision for general computer vision. So the standard, as I mentioned earlier, it's already published, and we are looking to publish more vertical area relevant standards, such as in medical domain and in finance domain. The first open source software, Fate, is becoming very popular. It's used by many organizations to extend as the central system, and they can build on top of it to extend into their own commercial or non-commercial systems. There are also open data source available, such as in VBank, we open sourced a Fed vision computer vision system. In Carnegie Mellon University, there are over 100 data sets that's open sourced. In University of Southern California, there's a system which is available for people to test on. There are also great many open source platforms beyond Fate, such as Google's TensorFlow system, in PyTorch, in Uber, in OpenMind, and in TEE systems and Baidu's Paddle system. So finally, I want to give a detailed example of a medical application. So here is a Chinese patient information. The patient may go through different hospitals in different tests, and the records, that is the data, are located in these different sites. And the time span is over maybe several years. Now, in a traditional way, this data cannot be easily combined because the hospitals safeguard the privacy, and they don't want to communicate with each other too much. But these cases, these tests point to very alarming scenario. In a sequence, they show that the patient, which is 50 years old female, is moving alarmingly towards stroke. And so whether we can predict the stroke event earlier can save lives. So globally, we can look at in different types of records are located in different places, in different hospitals, in different community annual check center, in different MRI labs, and so on. So we built a machine learning model which can take about half a year's test data from 6,000 patients in a time series, and build an A/B test version for stroke patient prediction. We wish to predict the stroke event earlier, and we categorized the severity into 10 classes, and we can see that these training data are distributed among these 10 classes to be used to train the model. The result, well, traditionally, to build such a model is very challenging because different hospitals hold different amount of the samples. For example, one hospital holds 130,000 samples, and the small hospital, such as the E hospital, holds only 11,000. So they are, in numbers, they are different. In distributions, they also non-AIED. The result of our initial test is very encouraging. For example, in the model accuracy improvement is over 80%. And for small hospitals, the improvement is great. And the paper is published in the XAI workshop and has generated a great number of interests. Now, I should also mention that federated learning just started as a research field. There are a large number of challenges which researchers can tackle. For example, there's this paper titled "How to Backdoor Federated Learning." So if a participant is a malicious user, it can potentially backdoor or using some kind of advanced machine learning algorithm to do data poisoning to influence the whole general model. Another potential difficulty is information leakage using GAN, using an adversarial model to simulate and to pretend the participant is a good party. There's also the challenge into how to lower the technology barrier of federated learning by introducing auto ML. So both University of Southern California and WeBank are researching on automatic federated learning, to encourage the non-technical people to make use of federated learning. Finally, I should mention that this field is paid attention by a great number of different fields, such as medical domain. I'm sure in education domain, people are more and more interested because data are similarly located in different devices, in different parties, and they don't want to share original data, while they want to build a common global model that is more powerful and is updated regularly. So for those, I encourage people to join the community and ecosystem and try out our open source software. Thank you.